A single electron enters a dark laboratory aimed at a barrier with two narrow openings. Nothing about it looks dramatic. There is no explosion, no cosmic scale. No telescope pointed at the edge of time. Just a particle, a wall, and a screen waiting in silence. But inside this small experiment, one of our oldest instincts about reality begins to fail. The instinct says that a thing must be somewhere doing something definite, whether or not anyone checks. Quantum mechanics does not let that instinct survive untouched. If you have ever trusted the idea that the world simply has its properties before we measure them, leave that intuition in the comments. This story begins exactly where that certainty starts to crack. The experiment is called the double-slit experiment. Its design is almost childishly simple. Send light electrons, or even larger quantum objects, toward a barrier with two openings. Behind the barrier place a detection screen. If ordinary particles were passing through, you would expect two bright bands on the screen. One band behind the left slit, one band behind the right slit. That would be the clean classical answer. Tiny objects move through one opening or the other. They land where their path takes them. Reality behaves like a line drawn from source to screen. But when the experiment is done without checking which slit the particle passes through, the screen does not show two bands. It shows many. Bright and dark stripes appear across the detector. This is an interference pattern, the signature of wave behavior. A wave can pass through both slits, spread outward, overlap with itself, and create regions where its peaks strengthen each other and regions where they cancel. Water does this. Sound does this. Light does this. The shock is not that waves interfere. The shock is that single particles do it too. Send one electron at a time, not a crowd, not a stream dense enough to hide collisions. One electron, then another, then another. Each electron lands as a single dot on the screen. A dot is particle-like, yet after thousands of dots accumulate, the same interference pattern slowly appears. The pattern builds itself from individual arrivals. Each electron seems to contribute to a wave pattern as though it had access to both paths. The particle arrives in one place, but its probability behaves as if it traveled through two. This is the first fracture. The electron is not simply a tiny marble. For a long time, the classical imagination could still try to escape. Perhaps the electron really went through one slit, but some hidden wave guided it. Perhaps it had a secret path. Perhaps the pattern only looks strange because we are missing details. So physicists ask the obvious question. Which slit did the electron actually pass through? Put a detector near the slits. Let it record the path, make the hidden journey visible, and then the interference disappears. The screen no longer shows many alternating bands. It begins to show the pattern expected from ordinary particles. One distribution from the left slit, one from the right. The act of finding out which path was taken destroys the wave-like result. The experiment has not been changed in some poetic way. A physical detector was added. Information about the path became available. And the universe gave a different kind of answer. This is where popular explanations often go wrong. They say consciousness changed reality. They imagine a human mind staring at the apparatus forcing nature to obey. That is not the careful physics. In laboratory language, observation does not mean a person becoming aware. It means interaction. To know which slit an electron passed through, something must interact with it. A detector must absorb, scatter, or exchange energy with the system. The electron is not being watched from outside reality. It is being touched by reality. Observation is not passive. That sentence matters more than it first appears. In everyday life, looking feels harmless. You open a drawer and see what was already there. You unwrap a present and reveal the object inside. You check the sky and discover whether it is raining. The classical world teaches us that measurement uncovers pre-existing facts. The fact exists first. The measurement comes second. Quantum experiments put pressure on that order. They suggest that at least at the microscopic level, some properties are not simply waiting in a hidden box. This does not mean anything you imagine becomes real. It does not mean desire bends electrons. It does not mean your thoughts select the outcome. The double-slit experiment is not a license for mystical shortcuts. It is stranger and stricter than that. It says that the conditions under which a question is physically asked help determine what kind of answer nature can give. Ask for interference, and the system behaves one way. Ask for path information, and a different structure appears. The answer is tied to the question. A camera could record the path. A detector could record the path. A grain of photographic material could record the path. No human needs to be present at the moment of interaction. The crucial event is not awareness floating above matter. It is the creation of a physical record. Something in the world becomes correlated with the electron's path. Once that happens, the delicate possibility of interference is lost, at least for that setup. Here the old picture begins to lose authority. The old picture says reality is like a stage. Objects stand on it with definite properties. Observers enter later and inspect the scene. Quantum mechanics does not fit that stage so easily. It does not remove the world. It does not make reality imaginary. But it does make the observer broadly understood as the measuring arrangement, part of the event. The apparatus is not outside the story. It helps decide which story can be told. The small scale is important. You do not see chairs passing through two doors at once. You do not see stones creating interference patterns in your living room. The world of tables, hands, buildings, and planets behaves with overwhelming classical stability. That stability is real at our scale. It is why engineering works. It is why bridges stand. It is why you can place a cup on a table and expect it to remain there. Quantum mechanics does not erase ordinary reality. It explains why ordinary reality is a special surface of something deeper. But the surface is not the foundation. At the foundation, a particle may not carry all the definite properties our intuition expects. Its position, path, and behavior depend on the experimental context in which those properties are forced into clarity. This is not just ignorance. It is not merely that we lack better instruments. The best tested theory in physics tells us that the possible outcomes are encoded before measurement, while the specific outcome appears only when the system is measured. The screen in the darkroom keeps collecting dots. Each dot is definite. Each arrival is real. Yet the pattern behind those dots speaks a language older intuition cannot translate. It says that reality is not simply revealed. It is also, in a precise physical sense, enacted through interaction. The first lesson is not that mind creates the world. The first lesson is colder and deeper. Measurement is part of reality's machinery. And once that is admitted, the next problem becomes unavoidable. If a detector can force a result, what exactly counts as a detector? Where does the quantum possibility end and the definite world begin? Place a small detector beside one slit and the experiment changes. Not because a human eye has entered the room. Not because attention has become magical. The detector may be a cold device, a crystal, a circuit, a piece of matter with no awareness at all. It sits there silently. It does not wonder. It does not choose. Yet the interference pattern vanishes. The old intuition says a measurement is only a report about what happened. Quantum physics makes that too simple. A measurement is not merely a report. It is an event inside the physical world. To find out which slit an electron passed through the apparatus must interact with it. There is no perfectly ghost-like way to obtain information. A photon may scatter from the electron. A detector may absorb energy. A field may become correlated with the particle's path. Something has to touch the system even if the touch is incredibly small. The tiny touch matters because quantum interference depends on coherence. Coherence is the fragile phase relationship between alternatives. It is what allows the two possible paths to behave like parts of one wave. Think of two ripples spreading across a still pond. If their timing remains aligned, they can overlap and make a pattern. Peaks meet peaks. Peaks meet troughs. Bright and dark bands appear on the screen. But if one path leaves a physical mark in the world, the two alternatives are no longer cleanly combined. The world has learned something about the path. The system has become entangled with the detector. The interference is no longer available in the same way. The path was not merely seen, it was recorded. This is the correction that must come early, because without it, the entire subject becomes polluted by slogans. Quantum observation is not ordinary looking. It is not human curiosity shining from a mind into the void. It is a physical coupling between systems. In a laboratory, the word observer can mean a machine. It can mean a photographic plate. It can mean a molecule in the surrounding air. It can mean any system that carries away information about what happened. The observer is not necessarily conscious. The observer is whatever makes the alternatives physically distinguishable. That sounds like it should remove the mystery. And for many practical purposes, it does. Engineers building quantum devices do not need to invoke consciousness. Experimental physicists controlling photons, ions, superconducting circuits, or atoms mostly talk about isolation, noise coupling, and information leakage. If you protect the system from uncontrolled interaction, quantum behavior can persist. If you let the environment gain information, the quantum pattern fades. This is not a vague philosophical claim. It is a working rule behind quantum computing, quantum cryptography, and precision measurement. The fact has consequences. Quantum systems are not strange because they are watched by minds. They are strange because information has a physical cost. To know something about a quantum system, the world must become correlated with it. And once that correlation exists, other possibilities cannot interfere as before. Information is not weightless, it leaves tracks. A detector is a track-making machine. This is why the popular phrase consciousness collapses. The wave function is at best misleading. Standard quantum mechanics does not require a person to stare at the apparatus. The pattern can disappear even if the data is never read. It can disappear because the detector has become correlated with the path. Whether anyone checks the record later is not the essential point. The physical availability of path information is enough to change the behavior. But this careful answer does not make the problem disappear. It only moves it into sharper focus. If measurement is interaction, then ordinary matter is constantly measuring ordinary matter. Photons from the room strike dust grains. Air molecules collide with surfaces. Heat radiation leaks from every warm object. The world is full of tiny interactions, and each one spreads information. That is why large objects look definite. They are not delicately isolated waves. They are violently entangled with their surroundings. A chair in a room is being struck by countless photons and air molecules. Every moment information about its position is being scattered into the environment. The light bouncing off it reaches your eyes. The air around it carries thermal traces. The floor records pressure. The chair is not sitting in a quantum monastery protected from contact. It is immersed in a storm of physical records. That storm makes it behave classically for all practical purposes. Here the scale changes. The electron in the dark experiment can be isolated well enough to show interference. A grain of dust in sunlight cannot. Its quantum phases are dispersed into the environment almost instantly. A human body warm and wet and electrically active is vastly farther from isolation. Every cell exchanges heat, light, molecules and vibrations with its surroundings. At that scale, quantum delicacy is buried under a flood of interactions. This is why you do not see yourself split into visible alternatives when choosing a door. The ordinary world is stable because it is noisy. Yet the phrase for all practical purposes hides a deep edge. Practical disappearance is not necessarily fundamental disappearance. When a detector interacts with an electron, the equations of quantum mechanics can describe the electron and detector together as one larger quantum system. The electron path and detector record become linked. In the mathematics, the possibilities are not simply erased. They become distributed into a bigger structure. The interference becomes inaccessible locally, but the total quantum description may still contain all branches together. This is where the reassuring explanation starts to tremble. Saying the detector measured it works beautifully in the lab. It predicts what we see. It tells us how to build devices. It keeps mystical claims away. But the detector itself is made of atoms. Those atoms are quantum systems. They obey the same underlying rules. So why does adding a detector create one definite result instead of merely spreading the quantum state into the detector? This is not a trick question. It is the door to the measurement problem. At the human scale, the answer feels obvious. The detector clicks. A number appears. A mark is left. Someone reads the result. Reality has become definite. But if we insist on treating every part of the experiment by the same quantum equations, the click itself needs explanation. The machine is not outside physics. The screen is not outside physics. The notebook is not outside physics. The observer's body is not outside physics. So the second lesson is more precise than the first. Consciousness is not needed to destroy the visible interference pattern. Physical interaction is enough. But physical interaction alone does not yet explain why one outcome becomes the outcome we experience. The mystery has not vanished. It has changed address. What began as a question about a particle near two slits now becomes a question about the boundary of reality itself. If every measuring device is also quantum matter, then the next question is not what the detector sees. The next question is why the detector ever has a single definite story to tell. Imagine the electron reaches the detector, and the detector clicks. In the ordinary laboratory story, that is the end. A result has appeared. The path is known. The interference is gone. The screen, the machine, and the scientist all agree that something definite happened. But now slow the scene down and refuse to grant the detector any special status. Look at it not as a magical border between possibility and fact, but as matter. It is built from atoms. Its atoms are governed by quantum mechanics. Its atoms are not exempt from the same rules that made the electron strange. This is where the measurement problem becomes serious. The equations do not say that a detector is outside the quantum world. They do not contain a line that says small things obey superposition, but large laboratory instruments automatically produce reality. The detector is a physical system. The electron is a physical system. When they interact, quantum theory says they can become entangled. The electron going through the left slit becomes linked with the detector recording left. The electron going through the right slit becomes linked with the detector recording right. Instead of destroying the superposition in the deepest mathematical description, the interaction can spread it. The possibility does not end. It grows. This is the von Neumann chain, named after John von Neumann, one of the great mathematical architects of quantum theory. The chain begins with a quantum system in more than one possible state. Then it interacts with a measuring device. If the device is treated quantum mechanically, it becomes correlated with those alternatives. Then another device observes the first device. That second device also becomes correlated. Then light from the device reaches an eye. The eye is made of atoms. It enters the chain. Then neural signals reach a brain. The brain is made of atoms too. In principle, the chain keeps extending. At each step, the classical story says, now the result is definite. But the quantum equations, if applied universally, do not clearly say that. They say the correlations spread from system to apparatus, from apparatus to environment, from environment to observer. The superposition is not obviously cut off by a switch, a needle, a display, or a notebook. The wave-like possibility becomes entangled with more and more of the world. Picture a row of mirrors in a dark hallway. The electron reflects into the detector. The detector reflects into the screen. The screen reflects into the eye. The eye reflects into the brain. Each mirror seems to pass the question onward. Where did the single fact appear? Which mirror stopped reflecting possibilities and began showing only one world? That question is not answered by the standard equation alone. The Schrödinger equation describes a smooth continuous evolution of the quantum state. It is deterministic. If you know the state now, the equation tells you how it changes. But the experience of measurement seems different. Measurement gives one outcome, not a smooth blend, not a visible superposition of mutually exclusive results. You see the detector click left or right. You do not experience both. Here lies the conflict. The mathematics gives us evolving possibilities. Experience gives us definite facts. Both are unavoidable. A common textbook approach handles this by adding a rule. Before measurement, use the wave function. During measurement, apply the Born rule to get probabilities. After measurement, update the wave function to match the observed result. This works extraordinarily well. It lets physicists predict experiments with astonishing accuracy. But as an account of reality, it leaves a wound. The collapse is inserted as a rule of use. It is not clearly derived from the same continuous dynamics that governs everything else. This does not mean quantum mechanics is wrong. It means quantum mechanics has a foundational question at its center. Its predictions are among the most successful in science. The difficulty is not practical failure. The difficulty is interpretation. What exactly is the wave function? Is it a real physical object? Is it a tool for predicting observations? Does it ever truly collapse? Or does it only appear to collapse because observers are inside one branch of a larger quantum state? The detector click looks simple because our world is large, warm, and noisy. But simplicity at the surface can hide a deep unresolved structure. A thermometer gives one reading. A Geiger counter makes one sound. A camera records one image. At the level of everyday experience, definiteness is not optional. Without it, memory, language, and science itself would fall apart. Yet, when we ask where definiteness enters the theory, the answer becomes surprisingly difficult. This is the limit of intuition. Human minds evolved to track stones, animals, fire faces, and weather. We did not evolve to imagine a laboratory, a detector, and a brain as one quantum system. We are very good at objects. We are poor at global states, so we smuggle in a boundary. We say the electron is quantum, the detector is classical, and the observer is outside the problem. That boundary works in practice, but the deeper question asks whether the boundary is fundamental or only convenient. The old worldview depends on a clean separation. There is the thing measured, there is the measuring device, there is the person reading it. Each has its role. Quantum mechanics blurs the separation. If the measuring device is made of the same quantum stuff as the thing measured, then the act of measurement cannot be explained by simply pointing to the device. The device is part of the same puzzle. The machine is not the end of the chain. It is another link. This is why the measurement problem has survived for nearly a century. Not because physicists forgot to think about it. Not because the experiments are vague, but because every proposed solution changes the picture of reality in a major way. Some approaches say collapse is a real physical process. Some say there is no collapse, only branching. Some say the wave function is not a thing in the world but a tool for organizing expectations. Some say the question itself is malformed if we demand a classical story behind quantum events. Each option pays a price. Real collapse may require new physics. Many worlds keeps the equation clean but multiplies reality beyond common sense. Information-based interpretations preserve humility but refuse to give a simple picture of what exists independent of observation. There is no free answer. The measurement problem is not a small technical gap. It is a crossroads where different ideas of reality split. And the most uncomfortable part is this. You never experience the chain. You experience the result. Whatever the global quantum description might be, your lived world arrives already definite. A line appears on the screen. A number enters the notebook. A memory forms. The many possibilities have become one biography. That is the third lesson. The mystery is not that quantum systems can be strange. The mystery is that a world built from quantum systems feels so definite from within. The question has changed again. It is no longer only why interference disappears. It is why experience has a single face. And once that question is open, the oldest interpretation of quantum mechanics steps forward with an answer that is both practical and unsettling. Perhaps we should stop demanding a hidden story between measurements at all. A physicist places an instrument in front of nature and asks a question. Not a vague question. A carefully built physical question. Will this electron leave a mark here? Will this photon pass through this polarizer? Will this apparatus reveal wave behavior or particle behavior? In ordinary life, questions do not change the object being questioned in any deep way. Asking where a coin landed does not decide whether it landed heads or tails. But the Copenhagen interpretation asks us to abandon that comfort. At the quantum level, the way the question is physically asked helps define what kind of answer can exist. This interpretation grew from the work of Niels Bohr and the early architects of quantum mechanics. It is not one single perfectly fixed doctrine. Different physicists use the phrase in slightly different ways, but its central attitude is clear. Quantum theory is not a picture of tiny objects secretly moving along definite paths. It is a framework for predicting what can be said about measurement outcomes. Before measurement, certain properties are not merely unknown. They may be undefined. That is the cut in the old worldview. The property is not hidden. It is not yet a fact. Take the double-slit experiment again, but do not rush past the question. If the apparatus is arranged to reveal interference, the electron behaves in a way that cannot be explained as a simple particle taking one definite slit. If the apparatus is arranged to reveal which path, the interference disappears. Copenhagen does not say the electron is secretly a wave wearing a particle mask or a particle pretending to be a wave. It says the concepts wave and particle are limited tools. Each applies under a specific experimental arrangement. Neither captures the whole thing by itself. Bohr called this complementarity. Two descriptions can be mutually exclusive and yet both necessary. The wave description and the particle description do not fit together into one ordinary image. You cannot use them at the same time in the same experimental context. But you need both to account for the full range of phenomena. The electron is not comfortably one or the other. It is something our classical language cannot hold without splitting. Imagine trying to describe a shadow using only the words flat object and moving darkness. Each phrase catches something. Neither phrase is the thing itself. Quantum objects force an even harsher failure of language. They do not simply hide behind our words. They reveal that our words were built for a world of table stones and thrown objects. At the quantum level, a language arrives late and poorly equipped. This is not mysticism. It is discipline. Copenhagen refuses to invent an invisible classical story just to satisfy intuition. It says we should speak only about what experiments can meaningfully define. If no measurement arrangement gives a definite answer to which slit while preserving interference, then demanding both answers at once may not be profound. It may be asking nature a question that cannot be physically posed. The limit is subtle but important. Copenhagen does not prove that nothing exists between measurements. That stronger claim depends on how one phrases the interpretation. What it does say, in its cautious form, is that quantum mechanics does not allow us to assign all classical properties to a system independent of the measurement context. The theory gives probabilities for outcomes. It does not give a film strip of hidden events behind the observed result. The universe may not be a movie. It may be a set of answers to possible experiments. That sentence is dangerous if handled carelessly. It does not mean the moon appears only when a person looks at it. Macroscopic objects are stabilized by countless interactions with their environment. Their properties become effectively definite long before human attention arrives. Copenhagen is not an invitation to deny the ordinary world. It is a warning against projecting ordinary definiteness down into a domain where the experiments reject it. The old intuition says a good theory should tell us what is happening at every moment. Copenhagen says, perhaps, that demand itself is inherited from classical physics, not from reality. In classical mechanics, a particle has a position and velocity at all times. The equations trace its path like a pen line across paper. Quantum mechanics gives something different. It gives a wave function probabilities and rules for measurement. If we insist that this must conceal a familiar story underneath, we may be forcing the universe into a costume it has already refused to wear. This is why Bohr's view felt so radical to Einstein. Einstein wanted a reality that existed with definite properties, whether measured or not. He believed physics should describe what is, not only what can be observed. Bohr answered with a different standard. Physics concerns what we can meaningfully say about nature, and what we can meaningfully say depends on the whole experimental arrangement. The disagreement was not about equations. Both men understood the predictions. The disagreement was about reality itself. The fact is clear, quantum experiments do not support a simple picture where all properties sit fully formed before measurement. The consequence is physical. Measurement context cannot be treated as a mere detail. It helps decide which properties can become definite. The existential consequence is quieter but larger. The world may not be made of ready-made facts waiting for consciousness or instruments to uncover them. Some facts may be born only when reality is forced into a particular relation. A fact can be an event, not just a possession. Still, Copenhagen pays a price. It draws a practical line between the quantum system and the classical apparatus, but it does not fully explain why that line exists. It tells us how to use the theory. It protects us from false images. It keeps prediction tied to experiment, but it can feel like a refusal to answer the deepest question. What is happening when nobody measures? What is the wave function describing? Is indeterminacy a feature of the world or a feature of our description? Copenhagen often responds by saying that some of these questions may be empty unless tied to possible measurements. That answer is powerful. It is also unsatisfying. It disciplines thought. But it leaves the imagination hungry. It saves physics from bad metaphysics, but perhaps by closing a door too quickly. And yet its core lesson remains difficult to escape. At the quantum level, the world does not behave like a warehouse of pre-existing labels. The label appears through an encounter. The instrument. The question and the system form one event. You cannot always separate what the thing is from how the thing is asked to appear. This is the fourth lesson. Reality may be less like a collection of objects and more like a grammar of possible answers. But if Copenhagen avoids the collapse problem by refusing to describe the hidden process, another interpretation takes the opposite path. It keeps the equation, removes collapse entirely, and accepts a price so large that common sense almost cannot carry it. Suppose the detector clicks left. In the room, the result feels final. The screen says left, the notebook says left. The scientist remembers left. The other possibility seems to have disappeared. But Hugh Everett asked a dangerous question in the 1950s. What if it did not disappear? What if the equation never broke? What if the wave function kept evolving exactly as quantum mechanics says, smoothly and continuously? And the only reason we see one result is that we are now inside one part of a much larger reality. This is the many worlds interpretation. It begins with a refusal. Do not add collapse. Do not insert a special measurement rule. Do not divide the universe into a quantum system on one side and a classical apparatus on the other. Treat everything as quantum. The electron, the detector, the room, the scientist, the brain, the notebook, the planet, the universe. Let the Schrödinger equation apply without exception. Then ask what follows. What follows is not comfortable. If an electron has two possible measurement outcomes, the combined system evolves into a state containing both. In one branch, the detector records left. In another branch, the detector records right. In one branch, the scientist sees left and forms a memory of left. In another branch, a counterpart of that scientist sees right and forms a memory of right. There is no mysterious collapse selecting one outcome from many. There is only branching. Every outcome allowed by the quantum state is realized in a separate branch of reality. The universe does not choose. It divides. This sounds like science fiction because ordinary imagination tries to picture branches as physical worlds splitting like roads in space. That image is too crude. In many worlds, the branches are not necessarily universes floating beside each other like bubbles. They are components of the universal wave function that no longer interfere because decoherence has separated them. Once information about the outcome spreads into the environment, the branches become effectively independent. They stop talking to each other. They become mutually unreachable histories. The key fact is decoherence. When a measurement result becomes entangled with the detector, the air, the light, and the surroundings, interference between different outcomes becomes practically impossible. For an observer inside one branch, the other branches are gone for all practical purposes. You cannot step sideways into them. You cannot send a message to them. You cannot look through a crack and see another version of the laboratory. They are not nearby in ordinary space. They are separated in the structure of the quantum state. This gives many worlds its power. It solves the measurement problem by denying that there is a special measurement event. Nothing collapses. Nothing supernatural happens when a detector clicks. The same equation governs everything. The price is that all outcomes exist. The apparent randomness of measurement becomes the experience of an observer finding themselves in one branch rather than another. Probability becomes a question about self-location inside a branching structure. That price is enormous, but it is not irrational. Many physicists are drawn to many worlds because it is mathematically clean. It does not require a vague boundary between quantum and classical. It does not require consciousness. It does not add a new physical collapse mechanism. It takes the formalism seriously and asks us to pay the metaphysical cost. If the wave function says both outcomes remain, then perhaps both outcomes remain. Common sense is not allowed to veto the equation just because the result feels too large. Still, the interpretation faces hard questions. If every possible outcome happens, what exactly do probabilities mean? Why should an observer expect results according to the Bond rule? The rule that connects wave function amplitudes to observed probabilities. Many worlds defenders have proposed answers using decision theory symmetry and rational expectation. Critics argue that these answers are not fully satisfying. The debate is active. This is not a settled fact of physics. It is a serious interpretation with serious support and serious unresolved issues. That distinction matters. Experiments confirm quantum predictions. They do not directly confirm many worlds. The branching picture is an interpretation of why the predictions work. It is not the same kind of statement as saying electrons produce interference or Bell inequalities are violated. Those are experimental facts. Many worlds is a proposed ontology, a claim about what the mathematics means. It may be right, it may be wrong, it may be impossible to separate from rival interpretations by ordinary experiments. Its strength is elegance. Its weakness is excess. But excess can be deceptive. Ask which is more extravagant, one universe that randomly collapses without a known physical mechanism, or a universal wave function that never collapses but contains many branches. The first preserves common sense by adding an unexplained event. The second violates common sense by keeping the equation untouched. Both pay. The disagreement is about which cost is more acceptable. This is why the measurement problem is not just a technical puzzle. Each proposed solution protects one principle by sacrificing another. Copenhagen protects experimental humility but leaves the hidden story incomplete. Objective collapse protects one shared outcome but modifies the quantum law. Many worlds protects the law but expands reality beyond ordinary imagination. There is no path through the problem that leaves the old worldview intact. Picture a tree at night. Not a tree made of wood, but a tree made of histories. Each quantum event is a fork too small to notice. A photon absorbed here, a nucleus decaying there, a molecule scattering in a slightly different direction. Most branches do not contain dramatic alternate lives. They contain tiny microscopic differences that spread into the environment. But over time, small differences can become large. In the many worlds picture, reality is not a single road through possibility. It is the entire branching structure. The old intuition wanted the world to be one story. Many worlds says the story may be larger than one reader. Yet even here we must be careful. Many worlds does not mean every fantasy exists. It does not mean anything you imagine becomes real. It does not mean impossible events happen somewhere. The branches are constrained by the quantum state and by the laws of physics. The interpretation is not a permission slip for wishful thinking. It is a rigorous attempt to avoid collapse by accepting the full consequence of quantum evolution. The existential consequence is strange but precise. If many worlds is right, the self you experience is not the whole story of the physical process. It is one continuation among many. Your memory feels singular because it belongs to one branch. The other outcomes are not experienced by you here, but by counterparts embedded in other decoherent branches. Identity becomes less like a single solid thread and more like a river splitting into channels that cannot rejoin. This does not change ordinary life. You still make choices, you still suffer consequences, you still inhabit one stream of experience, but it changes the background image of existence. The universe may not be a machine selecting one result. It may be a structure allowing all quantum consistent results to unfold while every observer finds themselves inside a single line of memory. The fifth lesson is not that many worlds is proven. It is that avoiding collapse does not make reality simpler. It only moves the strangeness from the moment of measurement into the size of existence itself. And once reality becomes that large, another question presses in. If branches become separate because interaction with the environment buries their coherence, then perhaps the real bridge between the quantum and classical worlds is not consciousness, not collapse, and not even measurement in the old sense. Perhaps it is the quiet violence of the environment itself. Leave the laboratory door open. Let the room breathe. Let stray photons pass through the apparatus. Let air molecules drift across the path of the particle. Let the table vibrate faintly under the building. Nothing dramatic happens to the eye. The detector still looks still. The room still looks ordinary. But at the quantum level, the experiment is being touched from every direction. Every tiny contact carries away a trace. Every trace weakens the fragile alignment that made interference possible. This is decoherence, And it may be the most important reason the world around you does not look quantum. A quantum superposition is not just a list of possibilities. It is a relationship between possibilities. The alternatives must remain coherent, meaning their phases must stay connected in a precise mathematical way. If they remain coherent, they can interfere. If they lose coherence, the interference fades. This is why a well-isolated photon can behave like a wave passing through two paths, while a warm object in a room behaves like a definite thing. The difference is not that one is magical and the other is normal. The difference is exposure. Quantum behavior survives in silence. The macroscopic world is never silent. Consider a grain of dust floating in sunlight. It seems small to us, almost nothing. But compared with an electron, it is enormous. It contains billions upon billions of atoms. Photons scatter from it constantly. Air molecules strike it from all sides. Heat leaks from it. Each interaction becomes a tiny record of where the grain is. The environment is not deliberately measuring it, but it is doing what a measurement does. It is becoming correlated with the grain's position. The information spreads outward too quickly to gather back. This is the central image of decoherence. A quantum secret leaks into the room. At first, the system may contain delicate alternatives, but once the environment becomes entangled with those alternatives, the phase relationship is dispersed into countless degrees of freedom. The information is not simply destroyed. In principle, it is spread across the air, the light, the walls, and the thermal motion of the room. In practice, recovering it is hopeless. You would have to reverse the state of an astronomical number of particles with impossible precision. The wave has not crashed. It has dissolved into the world. That distinction matters. Decoherence explains why different outcomes stop interfering with each other. It explains why a cat, a chair, or a detector does not visibly behave like a clean superposition. It explains why the classical world emerges so reliably from quantum rules. But it does not by itself explain why one particular outcome is experienced. It changes the problem, it does not erase it. It tells us why the branches no longer overlap. It does not tell us why this branch is the one that becomes your lived reality. This is the honest line. Decoherence is powerful, mainstream, and experimentally supported. It is essential to modern quantum theory. It is not the same as a complete solution to the measurement problem. Many physicists treat it as a major part of the answer, and for practical work, it often is. But at the foundational level, the final question remains: why does the world appear as one definite result rather than a collection of non-interfering alternatives? Still, decoherence changes the emotional shape of the mystery. It removes the need to imagine consciousness arriving like a spotlight to rescue the universe from vagueness. The environment is already there doing the heavy work. Long before a human mind reads a number, the apparatus has interacted with photons, air heat, cables, and surrounding matter. The result has become massively recorded. By the time awareness enters, the quantum delicacy has already been buried under a mountain of correlations. This is why the brain is not a simple quantum measuring wand. A human brain is warm, wet, chemically active, and densely connected to its environment. Neurons fire through electrochemical processes. Molecules collide. Ions move. Heat spreads. Any delicate quantum phase in such a system is usually expected to disappear extremely quickly. There are serious debates about special quantum effects in biology, and some limited quantum processes do appear in living systems. But ordinary human thoughts are not known to preserve laboratory-style superpositions across the scale of conscious decisions. This does not make consciousness unimportant. It makes the claim narrower. Consciousness may still be one of the deepest open problems in science, but the disappearance of interference in ordinary measurement does not require invoking it. The room itself is enough. The air is enough. The scattered light is enough. The environment is an ocean of accidental witnesses. The witness need not know. It only needs to carry a trace. Here the old intuition changes again. We tend to think of reality becoming definite because someone looks. Decoherence suggests a different picture. Reality becomes classical looking because nothing can remain isolated. The world is a web of uncontrolled interactions. Every large object is being continuously imprinted into its surroundings. Its position, shape, temperature, and motion are broadcast into the environment. Not perfectly, not metaphysically, but overwhelmingly enough that interference between macroscopic alternatives becomes inaccessible. Imagine trying to keep a candle flame perfectly still in a storm. The flame is the quantum phase. The storm is the environment. For a single atom in a carefully shielded trap, the storm can be reduced. Physicists can cool, isolate, and manipulate quantum systems with extraordinary precision. That is how quantum computers and atomic clocks become possible. But for ordinary objects, the storm never stops. The classical world is not a separate kingdom. It is what quantum systems look like when the storm has scattered their coherence everywhere. The scale translation is brutal. A single particle can be protected. A microscopic system can be coaxed into interference. But a coffee cup on a desk is coupled to a number of environmental interactions beyond imagination. Light from the room scatters from it. Air presses against it. Heat radiates from it. The cup is not waiting to be measured. It is being measured by the universe continuously. This is a controlled reality-breaking claim. The world looks definite not because it is simple, but because it is too entangled with everything around it for its quantum alternatives to remain visible. Yet that answer has a shadow. If decoherence only hides interference, then the deeper unity of the quantum state may still be there in the mathematics. The branches no longer communicate, but they may not be fundamentally erased. The classical world may be an appearance created by lost access, not by the destruction of possibility itself. What looks like a single hard fact may be a local perspective inside a much larger quantum structure. The sixth lesson is therefore double-edged. Ecoherence explains why reality appears stable, solid, and classical. But the very explanation depends on the environment swallowing quantum information so completely that we can no longer follow it. The ordinary world is not the opposite of the quantum world. It is the quantum world after its delicate patterns have been scattered beyond recovery. And if information can be scattered across the environment, another question becomes unavoidable. What happens when the timing of measurement itself is changed? What happens when nature seems to decide not only what is seen now, but what kind of path the particle can be said to have had send a photon into an apparatus and delay the decision into Tononi? That is the strange instruction. Do not choose at the beginning whether you want to know its path or see interference. Let the photon already enter the experiment. Let it already pass the crucial region. Let it already be on its way toward the final detectors. Only then decide what kind of measurement will be made. In everyday logic, this should be too late. The photon's path should already be settled. But quantum experiments do not respect that comfort as easily as we expect. This is the delayed choice idea associated with John Wheeler. Wheeler was not trying to make physics mystical. He was trying to sharpen the double-slit problem until the old picture had nowhere left to hide. If a photon behaves like a wave when no path information is measured, and like a particle when path information is measured, when does it decide which behavior to show? At the slits at the detector. At the moment an experimental arrangement becomes irreversible. The delayed choice experiment presses directly on that question. The setup can be made in different ways. In one version, the experimenter can choose whether to preserve information that allows interference or to obtain information about which path was taken. The crucial point is timing. The choice of measurement arrangement is made after the photon has already passed the point where, in a classical story, it would have needed to be either wave-like or particle-like. Yet the result still matches the final measurement context. If the arrangement reveals interference, the photon is described as having behaved wave-like. If the arrangement reveals path information, the photon is described as having behaved particle-like. The past does not behave like a fixed little movie. That sentence must be handled carefully. Delayed choice experiments do not prove that human intention travels backward in time. They do not let us send messages into the past. They do not make time travel available. What they do challenge is the assumption that a quantum object must have carried a definite classical history before measurement. The experiment suggests that asking which path the photon really took may be the wrong kind of question unless a measurement context makes that path a physical fact. Here is the correction. The photon is not a tiny bead that secretly chose one mode and waited for us to discover it. It is described by a quantum state that can support different experimental outcomes depending on how it is measured. When the final arrangement is chosen, the whole experimental context defines which kind of statement can be meaningfully made. The delayed choice feels retroactive because our minds demand a classical history. The quantum formalism does not need the photon to carry that history in advance. This is where Wheeler's phrase participatory universe becomes powerful and dangerous. Powerful because it captures the idea that observation is not a passive window onto a fully pre-written world. Dangerous because it is easy to exaggerate. Participation does not mean imagination creates facts. It means measurement arrangements help define which facts become available. The universe is not being rewritten by a human wish. It is being forced into a definite record by a physical interaction. The difference matters. A wish is not a measurement. A detector is not a dream. Wheeler extended the idea to a cosmic scale with a thought experiment involving light from a distant quasar. Imagine a photon leaving a quasar billions of years ago. Between that quasar and Earth sits a massive galaxy. The galaxy's gravity can bend light around it, creating two possible routes toward us. If an observer sets up equipment to determine which route the photon took, the result looks path-like. If the equipment instead allows the two routes to be combined in a way that reveals interference, the result looks wave-like. The choice is made now long after the photon began its journey. The image is almost unbearable. A particle of light leaves a remote source before life on Earth becomes complex. It crosses cosmic distance. Then an experiment performed today helps determine what kind of history can be assigned to its journey. Again, this does not mean the human observer changes an already written past. It means the past of a quantum system may not contain every classical fact we want to place inside it. Some facts become facts only when the conditions for recording them exist. The scale has changed from a tabletop to the sky. The crack is the same. At this point, the old intuition tries one more defense. Maybe the photon had a definite path all along, and the experiment only reveals different information depending on what we choose to measure. That sounds reasonable, but quantum experiments repeatedly resist simple hidden history explanations. The full challenge becomes sharper when combined with other results, especially entanglement and bell-type experiments. Delayed choice alone does not settle every interpretation. It does not force one philosophical conclusion. But it does make one thing harder to maintain the belief that quantum objects always carry complete classical stories before measurement. This is the limit of what the experiment proves. It supports the quantum prediction. It undermines naive realism about pre-existing paths. It does not prove consciousness creates the past. It does not prove all histories are equally real in a mystical sense. The honest claim is narrower and stronger at the quantum level. The history we can assign to a system depends on the measurement framework used to extract facts from it. That is enough to disturb the foundation. Because human beings live inside stories, we think in sequences. First this happened, then that happened, then the result appeared. Causality feels like a line. Memory feels like proof that the past was always definite. But quantum mechanics teaches us that the past of a microscopic system may not be fully describable as a chain of classical events. It may be more like a set of possible accounts, only some of which become meaningful when a measurement is performed. A history can be incomplete before it is recorded. This does not threaten your childhood memories. It does not make yesterday unreal. At the macroscopic scale, records are abundant. The environment continuously stores information. Footprints, photographs, scars, fossils, background radiation, and neural traces all stabilize the past we inhabit. Decoherence makes large-scale history extraordinarily robust. But underneath that stability, quantum theory suggests that definiteness is not the default raw material. It is an achievement of interaction, record, and context. The seventh lesson is that time itself becomes less simple when measurement enters the story. The issue is not whether the future magically changes the past. The issue is whether the past had the kind of definite microscopic detail classical intuition assumes. Wheeler's challenge is not a fantasy of backward causation. It is a disciplined attack on the idea that reality is always a completed archive. And once the archive begins to look incomplete, distance becomes the next assumption to fall under pressure. If a photon's history is not simply waiting behind it, what about two particles separated by half the universe? Can distance protect their independence? Quantum mechanics answers with one of the most tested and unsettling facts in modern science. Put two photons in the same quantum event, then send them in opposite directions. One goes left, one goes right. Let the distance grow. A laboratory bench, a city, a mountain range. In principle, the distance could be astronomical. Classical instinct says separation should give each particle its own private reality. Whatever happens to one should not instantly define the other. Space should protect independence. But entanglement shows that this instinct is not fundamental. Distance still limits signals. It does not fully restore separateness. Entanglement begins when two quantum systems are described by one shared state. Not two separate states that happen to match, but one state that cannot be split cleanly into independent parts. If the photons are prepared so their polarizations are linked, measuring one gives a result correlated with the other. If one is found vertical, the other may be found horizontal. Depending on the setup, the strange part is not correlation by itself. Ordinary objects can be correlated. Split a pair of gloves into two boxes, send one to Paris and one to Tokyo. And opening one box tells you instantly what is in the other. If you find the left glove in Paris, you know the right glove is in Tokyo. But entanglement is not a glove trick. The photons do not merely carry pre-written labels. That was Einstein's hope. In 1935, Einstein, Podolsky and Rosen argued that quantum mechanics must be incomplete. If measuring one particle lets us predict the state of the other, then perhaps the particles already carried hidden properties from the start. Quantum theory in this view was only a statistical surface. Beneath it, there would be a deeper local reality. Objects would have definite properties before measurement, and no influence would travel faster than light. This position is called local realism. Local means physical influence does not outrun light. Realism means properties exist before and independent of measurement. Together, they form the old picture in its most disciplined form. The world has its facts. Distance separates them. Measurement reveals them. Einstein did not reject quantum predictions lightly. He rejected the idea that reality itself could be so incomplete, so relational, so unwilling to assign properties before observation. For decades, this seemed like philosophy. Then John Bell changed the question. In the 1960s, Bell showed that local hidden variable theories must obey a certain limit, now called Bell's inequality. If particles merely carry pre-existing instructions, the correlations between measurement results cannot exceed a specific strength. Quantum mechanics predicts stronger correlations. This was the turning point. A debate about reality became an experiment. The experiment is conceptually simple. Create entangled particles, send them to separated detectors. Choose measurement settings, record the outcomes, compare the correlations. If Bell's inequality holds, local realism survives. If it is violated, the classical picture cannot remain intact. Over many decades, experiments increasingly closed loopholes. John Clauser performed early tests. Alan Aspect improved the timing and switching of measurement settings. Anton Zeilinger and others extended entanglement into quantum information experiments. In 2022, Clauser, Aspect, and Zeilinger received the Nobel Prize in Physics for this work. The result is not subtle. Bell inequalities are violated. The old picture fails. This does not mean faster than light messaging is possible. That point must be protected. When one observer measures a photon, the result appears random locally. The distant observer also sees random results. Only when they later compare records through ordinary communication do the correlations become visible. Since that comparison cannot travel faster than light, relativity's ban on faster than light signaling remains safe. Entanglement gives connection without usable superluminal communication. It is not a cosmic telephone, but it still changes the meaning of separation. The two photons cannot be understood as fully independent objects carrying all their properties separately before measurement. At least one piece of the classical package must be abandoned. Either realism fails in the old sense, or locality fails in a deeper non-signaling sense, or the entire framing has to be replaced. Different interpretations make different choices. Copenhagen tends to give up pre-existing definite properties. Bohmian mechanics keeps definite particles but allows a non-local guiding structure. Many worlds keeps locality in the wave function's evolution but changes what outcomes mean. Relational and information-based interpretations rework the role of facts themselves. The experimental fact is narrower than the philosophy, but it is strong enough to break the old certainty. The universe does not satisfy local realism. This is a controlled reality-breaking claim. It does not say everything is spiritually one. It does not say your feelings affect a star. It does not say distance is meaningless in everyday life. Distance still matters. It shapes causality, light travel, gravity, biology, memory, and every practical action. But at the level of quantum correlations, distance is not the absolute wall classical intuition imagined. Systems that share one quantum state do not become entirely separate just because space opens between them. Picture two bells cast from the same invisible metal. Strike one here and do not imagine that a sound travels across space to the other. That would be too simple. Instead, the deeper fact is that the two bells were never fully the two in the way our eyes assumed. Their separateness is real for many purposes, but the quantum description holds them together in one structure. The visual anchor is not a bridge. It is a single state stretched across distance. This matters because entanglement is not rare in principle. Whenever quantum systems interact, they can become entangled. A photon scattering from an atom, two particles produced in a decay, molecules colliding in air. The world is constantly generating correlations. In large, warm systems, decoherence scrambles these relationships so thoroughly that we do not experience them as clean quantum links. That is why your chair does not behave like an entangled photon pair in a controlled experiment. The unity is buried under noise. The separateness is emergent, stable, and useful. Here is the limit. Entanglement does not automatically give a mystical conclusion. It does not prove cosmic consciousness. It does not prove all minds are linked. It is a precise physical relation between quantum systems described mathematically and tested experimentally. If we turn it into a slogan, we lose the very thing that makes it powerful. The wonder is not that it confirms an ancient phrase. The wonder is that the most careful experiments humans have built force us to weaken a basic assumption, that real things must always possess complete independent properties of their own. The eighth lesson is that separateness is not as fundamental as it feels. Objects can be distant and still belong to one quantum description. Space can prevent signals without fully dividing reality into isolated pieces. The universe is not a pile of independent parts that later form relationships. At the quantum level, relationship can come first. And if relation can come before separateness, then matter itself must be re-examined. Perhaps the particles we imagine as little things are not things at all. Perhaps they are local disturbances in something wider, older, and less visible than any object our hands have ever touched. Take the smallest object you can imagine and make it smaller. Shrink a grain of dust until it becomes an atom. Shrink the atom until the nucleus is a dense point and the electron cloud becomes a faint surrounding blur. Shrink your imagination again, down to the electron itself. The old picture wants to stop there. It wants the electron to be a tiny bead, a final piece of matter, a little thing moving through space. Quantum field theory refuses that image. At the deepest level we currently know how to describe the electron is not a little object sitting in the universe. It is an excitation of a field that fills the universe. This is the next fracture in the classical worldview. Matter is not built from tiny solid things in the way bricks build a wall. Matter is made of patterns in fields. A field is something that has a value at every point in space and time. The electromagnetic field is one example. The electron field is another. There are quark fields, gluon fields, neutrino fields, and the Higgs field. In modern particle physics, every known elementary particle corresponds to a field. The field is the deeper entity. The particle is what the field does when it is excited in a quantized way. The ocean is not inside the wave. The wave is a behavior of the ocean. This analogy is useful, but it has a limit. An ordinary ocean exists in space. A quantum field is not a substance poured into space like water into a bowl. It is part of the mathematical structure used to describe physical reality itself. When physicists say an electron is an excitation of the electron field, they are not being poetic. They are describing the framework that underlies the standard model of particle physics, the theory that has survived some of the most precise tests ever performed. The visual change is enormous. Instead of imagining the universe as empty space containing particles, imagine invisible fields extending everywhere. What you call a particle is a local packet of energy in one of those fields. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. A quark is an excitation of a quark field. The thing you detect in a machine is local. The field from which it arises is not local in the same simple sense. It is present everywhere. This does not mean one electron is spread across the universe in the ordinary sense. A particular electron can be localized in a region. It can be measured, trapped, accelerated, or absorbed. But the field that makes electrons possible is universal. The electron in a laboratory and the electron in a distant star are not two separate kinds of substance. They are excitations of the same underlying field. The many arise from one continuous structure. Here the old intuition of objecthood weakens. We tend to think a thing has identity because it is made from its own private stuff. Quantum field theory suggests something different. Identity comes from a pattern of excitation and from the properties of the field. Every electron has the same charge, the same spin, the same mass, not because of factory-stamped identical beads, but because each electron is an excitation of the same field obeying the same rules. A particle is not a pebble. It is a repeated gesture of a field. The fact has direct consequences. In high-energy collisions, particles can be created and destroyed. This is not like breaking a marble into pieces or gluing pieces together. If enough energy is concentrated into the right field, an excitation can appear. If a particle meets its antiparticle, their excitations can vanish into other fields as photons or other products. Matter is not permanent little stuff being shuffled around. It is field energy changing form according to strict conservation laws. This is why particle accelerators do not simply look inside particles like microscopes looking inside cells. They create conditions under which fields reveal what excitations they can support. When protons collide at enormous energies, the collision energy can become new particles. The detector sees, tracks, showers, and decay products. Behind those marks is a deeper story. Fields being struck hard enough to produce rare patterns. The machine is not only a camera, it is also a forge. The Higgs boson discovery in 2012 is a powerful example. For decades, physicists predicted a field associated with how certain elementary particles acquire mass. The Higgs boson was the detectable ripple of that field. When experiments at the Large Hadron Collider found evidence for it, they were not finding a tiny ball called mass. They were detecting an excitation of the Higgs field. The result confirmed that an invisible field permeating space is not a decorative idea. It is part of how the known world gets its structure. But even here, caution matters. Popular explanations often say the Higgs gives everything mass. That is too simple. The Higgs field gives mass to elementary particles such as electrons and quarks, and to the W and Z bosons. But most of the mass in ordinary matter comes from the energy of the strong force inside protons and neutrons. The quarks inside a proton contribute only a small fraction of its mass. The rest comes from the energy of gluons and the dynamics of quantum chromodynamics. Your weight is not mostly Higgs field. It is mostly confined field energy. That correction is not a detail. It changes the image of the body. The mass of your hand is not a pile of tiny solid pellets. It is largely the energy of fields bound into stable patterns. A rock is not heavy because it contains miniature, hard grains of ultimate stuff. It is heavy because energy is trapped in configurations that resist change. Einstein's relation between mass and energy is not a slogan here. It is the deep accounting system of matter. The old worldview wanted substance. Modern physics gives process. There is a limit to this picture too. Quantum field theory is extraordinarily successful, but it is not the final theory of everything. It does not yet merge cleanly with gravity at all scales. It has parameters measured from experiment rather than fully derived from deeper necessity. It describes the known particles with stunning precision, but it does not explain dark matter. And it does not settle the measurement problem by itself. The field picture is powerful. It is not complete. Even so, it has already changed the meaning of existence. If particles are field excitations, then the world is less like a warehouse of objects and more like a vast musical structure, where what we call things are stable notes held long enough for bodies, stars, and memories to form. The solidity of matter is not denied, it is relocated. It becomes an emergent feature of field interactions, not the primitive foundation. The ninth lesson is that matter is not the bottom layer. The bottom layer, as far as our best tested theories reach, is a set of fields and the rules by which their excitations appear, interact, and vanish. What looks like a thing is a pattern with persistence. And once matter becomes a pattern in fields, emptiness can no longer mean what it used to mean. If fields are everywhere, then even a region with no particles is not truly nothing. The next shock is waiting in the place that classical physics called empty space. Remove everything from a small region of space. Pump out the air, block the dust, shield the chamber from light, cool it, seal it. Imagine the cleanest emptiness technology can build. Classical intuition says that when matter and radiation are gone, nothing remains except a blank stage. Empty space should be silent. It should do nothing. It should push on nothing, pull on nothing, create nothing, disturb nothing. Quantum field theory says this intuition is wrong. Empty space is not truly empty. It is the ground state of fields that cannot become perfectly still. This is one of the most difficult ideas to say without exaggeration. The quantum vacuum is not a crowded room full of tiny permanent particles popping in and out like sparks in a fire. That image is useful for intuition, but it can mislead. More carefully, the vacuum is the lowest energy state of quantum fields. Even in that lowest state, the fields possess fluctuations. They cannot have exactly zero motion and exactly zero uncertainty at the same time. The vacuum is not nothing. It has structure. Silence at the deepest level still trembles. The first clue came not from philosophy, but from precision. In hydrogen, the simplest atom, tiny shifts appear in energy levels that classical theory could not explain. One of these is known as the Lamb shift. It was measured in the 1940s and became one of the key successes of quantum electrodynamics. The electron in hydrogen does not exist in an empty background. It interacts with the fluctuating electromagnetic field around it. Those interactions slightly alter measurable energy levels. The change is small, but small is enough. A vacuum that changes an atom is not a meaningless void. Another clue is the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum. No battery. No obvious charge pushing or pulling. Yet the plates experience a tiny force drawing them together. One way to describe this is that the plates restrict which vacuum field modes can exist between them, while outside them more modes are available. The imbalance produces a measurable pressure. Empty space arranged with boundaries produces a force. The image is simple enough for a camera. Two silent plates facing each other in a chamber. Nothing visible between them. No hand, no spring, no wind, and still the vacuum presses. Nothing has consequences. Again, there is a limit. The Casimir effect is subtle and its full interpretation depends on careful quantum theory and material properties. It is not proof that free energy machines are possible. It is not a doorway to unlimited power. The vacuum has structure, but a structure does not mean easy extraction. Physics is precise here. The vacuum can produce measurable effects under specific conditions. It does not become a magical reservoir waiting for human desire. That boundary makes the fact stronger, not weaker. The wonder is not that the vacuum lets us do anything we want. The wonder is that the word empty fails at all. Classical emptiness meant absence. Quantum emptiness means the lowest allowed activity of fields. Even when particles are not present, the field remains. Even when the chamber is dark, the rules are still there. Even when nothing crosses the detector, the ground state is not a dead zero. The consequence reaches far beyond a laboratory plate. Vacuum energy sits at the center of one of the deepest unsolved problems in physics. When physicists try to calculate the energy of the quantum vacuum in a straightforward way, the result is wildly larger than what cosmology appears to allow. Not a little wrong. Not a factor that can be repaired by rounding. The mismatch is often described as one of the worst prediction problems in theoretical physics. Something about our understanding of vacuum energy, gravity, or both is incomplete. This is where the small chamber opens into the universe. Cosmological observations show that the expansion of the universe is accelerating. The term dark energy is used for whatever drives that acceleration. In the standard cosmological model, dark energy makes up most of the total energy budget of the universe. It behaves, at least in the simplest description, like an energy of space itself. But connecting that observed cosmic acceleration to the vacuum energy predicted by quantum field theory leads to an enormous mismatch. The vacuum is measured as cosmologically gentle, but calculated in naive quantum terms as catastrophically intense. The empty room has become a cosmic problem. This is a controlled claim, not a slogan. We do not yet know the final nature of dark energy. It may be a cosmological constant. It may reflect something more dynamic. It may point toward physics not yet discovered. But the tension is real. Empty space, once treated as the easiest part of the universe to understand, has become one of the places where our best theories fail to meet cleanly. Quantum fields and gravity both work brilliantly in their domains. At the vacuum, their marriage becomes troubled. The old intuition loses another layer. It thought matter was the active part and space was the passive container. Quantum theory reverses the emphasis. Space without particles is not a mere container. It is filled with fields in their ground states. Boundaries can change measurable forces. Atoms can feel vacuum fluctuations. Cosmology may depend on the energy associated with empty space. The stage is not passive. The stage participates. Picture a theater after everyone leaves. The seats are empty. The lights are off. The curtain is still. Classical physics would call that absence. Quantum physics asks you to listen more carefully. The floor is vibrating below hearing. The walls hold modes you cannot see. The silence has architecture. The theater is not performing a play, but it has not ceased being physical. That is what the vacuum does to the idea of nothing. It turns nothing into a question. And the question has an existential edge. Human beings often divide reality into presence and absence. Something is there or it is not. A body exists or it does not. A space is filled or it is empty. Quantum fields blur this division. Absence of particles is not absence of being. The ground from which particles arise is still physically rich. What we call nothing may be only the quietest form of something. This does not solve the ancient question of why there is something rather than nothing. It sharpens it. Physics can describe vacuum states, field fluctuations, and measurable effects. It can show that empty space is not simple emptiness. But it does not yet explain why the fields exist at all, why their laws have the form they do, or why the vacuum energy has the value cosmology suggests. The deepest nothing remains beyond the laboratory vacuum. The 10th lesson is that emptiness is not an absence beneath reality. It is part of reality's machinery. The vacuum is where fields remain when particles are gone. It is where silence becomes measurable. It is where our theories become most precise and most incomplete at the same time. And if matter is field excitation and emptiness is not empty, then the body holding this thought must also be reimagined. The next step is not in a distant accelerator or a sealed chamber. It is in the contact between your hand and a stone, where solidity itself becomes an emergent negotiation between fields. Press your palm against a stone. The sensation is immediate. Hardness. Resistance. A boundary that refuses to open. Your hand stops at the surface and the old intuition returns with force. Matter feels solid because matter is solid. The stone seems to be a compact object made from smaller compact objects all the way down. But that feeling is not the foundation. It is an effect. The stone does not stop your hand because tiny hard balls collide like miniature marbles. It stops your hand because quantum fields charges. And exclusion rules refuse to let certain patterns overlap. At first, the correction sounds familiar. Atoms are mostly empty space. The nucleus is tiny compared with the atom as a whole. The electron cloud occupies the surrounding region, not as a swarm of little planets, but as a quantum probability structure. If the nucleus were enlarged to the scale of a small seed in a stadium, much of the atom would still be open volume by ordinary visual standards. The image is useful, but it is not the full answer. If atoms are mostly empty, why does your hand not pass through the stone? The answer is not emptiness. The answer is resistance organized by quantum law. Two main effects matter here. The first is electromagnetic repulsion. The electrons associated with the atoms in your hand and the electrons associated with the atoms in the stone carry the same kind of electric charge. As the electron clouds approach, electromagnetic forces resist the compression. The second is the Pauli exclusion principle. This principle says that identical fermions, such as electrons, cannot occupy the same quantum state. When matter is pressed into matter, electrons are forced toward arrangements that are not allowed or that require more energy. The resistance grows. This is what solidity feels like from the inside of a human nervous system. Not contact between ultimate hard pieces. Not little surfaces touching in a tiny mechanical universe. Solidity is the macroscopic experience of quantum systems resisting overlap. The stone pushes back because fields and particles obey rules deeper than the visible surface. Your palm meets not a wall of stuff, but a wall of forbidden arrangements. Hardness is not primitive. Hardness is enforced. This changes the meaning of touch. When you touch a table, the atoms in your skin do not truly merge with the atoms in the wood. At ordinary conditions, their electron structures repel and reorganize before nuclei come anywhere close to direct contact. The sensation of touch is your nervous system interpreting electromagnetic resistance. Pressure receptors in your skin deform. Signals travel through nerves. Your brain constructs the feeling of a surface. What seems like direct contact is mediated by fields. This does not make the table unreal. It makes the table stranger. The table is real enough to hold a cup, real enough to bruise a knee, real enough to build a house. But its solidity is not the same kind of reality the old imagination assigned to it. It is stable, measurable, and dependable, yet emergent. It appears when vast numbers of quantum constituents interact under the right conditions. The surface is not fake. It is a higher-level truth built from deeper rules. Scale matters again. A single atom is not solid like a stone. A proton is not solid like a grain of sand. A human body is solid only because uncountable field interactions organize into a stable pattern. The ordinary world is made from effects that are individually invisible but collectively overwhelming. The same is true of temperature. One molecule does not have temperature in the everyday sense. A crowd of molecules does. Solidity is similar. It belongs to the organized many, not to an ultimate tiny brick. Now consider mass. The body pressing on the stone has weight. The stone pressing back has weight. It is tempting to imagine mass as the amount of substance packed inside an object. More stuff, more mass. But quantum field theory gives a deeper account. Some elementary particles acquire intrinsic mass through interaction with the Higgs field. That part is real and experimentally supported. The Higgs field matters. Without it, the known structure of matter would be radically different. But ordinary mass is not mostly Higgs. Most of the mass in protons and neutrons comes from the energy of the strong interaction. Inside protons and neutrons, quarks are bound by gluons and the dynamics of the strong force. The quarks themselves contribute only a small portion of the total mass. The rest is energy confined in the system. Energy, through Einstein's relation between mass and energy, appears as mass. The weight of ordinary matter is largely the weight of bound field energy. You are not heavy because you are filled with tiny solid pellets. You are heavy because energy has been trapped into form. The consequence is intimate. Your bones, blood, hands, and brain are not separate from the field-based universe described in accelerators. They are made from the same kinds of excitations, interactions, and constraints. A person is not an exception to physics standing above the quantum world. A person is an enormous, warm, stable pattern produced by the same deeper rules. The body is not less real because it is process. It is more astonishing because it persists at all. This is where caution is needed. Saying the body is a pattern of fields does not mean the self is an illusion in a careless sense. It does not mean pain is unreal, love is unreal, or responsibility is unreal. Higher-level realities can be real even if they are not fundamental. A melody is real though it is made from vibrations. A storm is real. though it is made from moving air and heat. A living body is real though it is made from fields, chemistry, memory, and metabolism. Emergence is not falseness. Emergence is how complexity becomes visible. Still, the old intuition has changed. The self no longer looks like a solid object sealed inside skin. The skin itself is a boundary maintained by molecular exchange, immune system's pressure, temperature, and constant interaction with the environment. You inhale atoms that were outside you. You exhale atoms that were inside you. Light strikes your retina. Sound reshapes your nervous system. Food becomes tissue. Heat leaves the body. The boundary is real, but it is not absolute. It is a living negotiation. The stone and the hand are not two sealed worlds. They are two patterns meeting. This is the 11th lesson. The solidity you trust is not a lie, but it is not the bottom truth. It is a macroscopic agreement produced by electromagnetic forces, quantum exclusion field energy, and biological interpretation. The body is not a lump of ultimate substance moving through a dead container. It is a temporary structure of the same universe that fills the vacuum, forms particles, entangles systems, and turns energy into mass. And now the final question can be asked without rushing. If observation is interaction, if matter is field excitation, if emptiness has structure, if separateness is not fundamental, and if the body itself is an emergent pattern, then what does it mean to exist at all? Not as a slogan, not as an escape from science, but as the quiet consequence of everything the experiments have already forced us to reconsider. Stand inside the universe and try to describe it from the outside. That is the impossible position every observer secretly wants. We want a view from nowhere, a clean diagram, a final map where particles, fields, measurements, bodies, minds, and galaxies all sit in their proper places. But quantum physics keeps removing the platform beneath that desire. It does not say reality is unreal. It says reality is not built in the simple way our instincts expected. The observer is not floating outside the scene. The observer is made from the scene. This is the final fracture in the old worldview. There is no official law called the quantum law of being. No equation in physics carries that title. No serious textbook says quantum mechanics has solved existence. That must be said clearly. The phrase can sound grand, but physics is stricter than grandeur. What we have are experiments, equations, and unresolved questions. The double-slit experiment shows that measurement context matters. Decoherence shows why the large world appears definite. Bell tests show that local realism cannot survive unchanged. Quantum field theory shows that particles are excitations of fields. Vacuum physics shows that emptiness has structure. Those are not metaphors. They are pressure points. Each one presses on a different assumption. The double slit pressures the belief that properties are always waiting, fully formed. The measurement problem pressures the belief that the transition from possibility to fact is already understood. Entanglement pressures the belief that distance guarantees independent reality. Quantum fields pressure the belief that matter is made of little solid things. The vacuum pressures the belief that nothing means no physical structure. None of these facts gives a complete philosophy of life. Together, they make the old mechanical picture too small. The old picture was powerful. It still works across ordinary scales. A stone remains a stone. A door remains a door. A bridge must be engineered correctly or it falls. Classical reality is not discarded. It is recovered as an approximation, an emergent layer, a reliable surface. But it is no longer the deepest portrait. Beneath that surface, the world is not a collection of self-contained objects moving through a passive emptiness. It is a network of fields, interactions, records, correlations, and emergent stability. Being looks less like a noun. It looks more like a process. That sentence can be made too poetic, so keep it grounded. An electron is not a tiny permanent bead. It is an excitation of a field. A measurement is not a passive glance. It is a physical interaction that creates a record. A solid body is not ultimate hard stuff. It is a stable result of forces, exclusion rules, chemistry, and perception. Empty space is not a dead container. It is a vacuum state with measurable effects. In every case, the thing we treat as simple turns out to be an event, a relation, or a pattern. The consequence is not that anything goes. Quantum physics is not a permission slip for fantasy. It does not prove that thought directly creates external reality. It does not prove that consciousness controls electrons by intention. It does not prove that every spiritual statement is secretly physics. The most honest lesson is narrower and stronger. Reality is more relational, less object-like, and less separable than everyday intuition suggests. That is already enough. The limit must remain visible. Interpretations of quantum mechanics still disagree. Copenhagen, many worlds objective collapse theories, Bohmian mechanics, relational views. And information-based interpretations do not tell the same story about what is ultimately real. Experiments constrain them, but they have not forced universal agreement. Consciousness remains an open scientific and philosophical problem. Vacuum energy remains deeply unresolved. Quantum gravity remains incomplete. The final theory is not in our hands. But ignorance is not emptiness. It is a boundary with shape. We know enough to know that the simple picture failed. We do not know enough to replace it with one final image. That is why the subject feels so powerful. It does not merely hand us answers. It teaches us which questions were too naive. What is a particle, not a little object in the old sense? What is empty space, not mere absence? What is measurement, not just looking? What is separation, not absolute at the deepest quantum level? What is solidity, not primitive substance? What is a human body, not an isolated lump, but a temporary, living organization of the same physical reality it observes? Now bring it back to the person listening. Your body is made from fields in patterned activity. Your senses receive a world already filtered by scale biology and interaction. Your memories rest on physical records. Your thoughts arise in a warm, classical-looking brain that is itself built from quantum matter. Even if ordinary thought is not a controlled quantum superposition, you do not stand outside reality to inspect it. You are one of the ways reality produces an inside view. That does not make you the center of the cosmos. It makes you a participant. Participation here does not mean command. It means embeddedness. You are not outside the system you are trying to understand. Every instrument humans build is made of the same fields it measures. Every equation is written by a brain made of the matter it describes. Every observation is an interaction inside the universe, not a message from beyond it. Science remains powerful precisely because it admits this and still finds stable patterns. It does not need a view from nowhere to discover truth. It needs repeatable contact with reality. So what does it mean to exist? Physics does not answer that in one sentence, but it has changed the terrain of the question. To exist is not necessarily to be a solid, separate thing with fixed properties sealed inside itself. To exist may be to persist as a pattern within fields, to interact, to leave records, to participate in relations, to arise from conditions and return into conditions. This is not a mystical escape from matter. It is matter understood more deeply than matter first appeared. The final lesson is not certainty. It is disciplined wonder. The universe is not less real because it is stranger than the old image. It is more real than the old image could hold. The stone remains hard. The vacuum remains quiet. The body remains yours. But now hardness is an emergent negotiation. Quiet is a field in its lowest state. The body is a temporary architecture of energy, matter, and memory. The familiar world has not disappeared. It has deepened. And perhaps that is the most honest ending. Quantum physics does not give us a neat law of being. It gives us a wound in the simple picture and then asks us to look through it carefully. What we see there is not chaos. It is a reality where objects are patterns. Emptiness is active distance, is limited measurement matters, and the observer is never completely outside the observed. The mystery is not a failure of knowledge. It is the ground from which deeper knowledge begins.